All right, we're here for AP Physics Linear Motion. I'm going to do problem 5, which this kind of odd question says, an object starts at rest at position 0 meters at 0 seconds. At 5 seconds, it's observed to be at this position, 40 meters, and have an instantaneous velocity of 11 meters per second. From this data, was the acceleration uniform or non-uniform? And explain. And then I kind of hint here, are the kinematics equations that we've been using applicable in this case? Why or why not? So we're going to go ahead and take a look at this. I'm starting from 0, 0, right? So if I did I'm going to draw the VT graph. Okay, this is problem 5, and let's start with the VT graph. Okay, velocity versus time. Okay, we're told that this object starts at 0, 0 at the origin, right? So work, right? And that 5 seconds later, it's at position 40 with a velocity of 11. So I'm going to go ahead. I'm going to mark this at 11 meters per second here. All right. I'm wishing I'd drawn. That's okay. Yeah, I'm kind of wishing I'd drawn an XT graph also first, actually. Oh well, that's life. That's okay. We can do that later. All right. So here's I like VT graphs. They're kind of in the middle between position and acceleration, and they can go kind of either direction from them. I really like VT graphs for analyzing anyway. So we're going to do this. Okay. Now we're going to go from here to here. Now, you know that if we had uniform acceleration, that would be a constant acceleration, then the VT graph would be linear. Why? Because the slope of a VT graph is the acceleration, how quickly you're changing velocity per second, right? Per unit of time. And so the slope's acceleration, if it's a constant acceleration, it'd be a constant slope, it'd be a straight line. And you see this graph would look like this. Except I missed, but you get it, right? It's going to be a linear graph, right? So that's what it would look like. Now, if this was a linear VT, then you say, well, gosh, on a VT graph, isn't the area under it the displacement? Right? And so if that area is the displacement, it's a triangle, so it'd be 1/2 base times height, half of 5, right, times 11. You say, well, that would give me a displacement of 55 divided by 2, 27.5 meters. You say, but wait a minute. In the problem, they told us the displacement was 40 meters. And you're like, what? This is less than 40 meters. So if it can't be uniform acceleration. If it had been a uniform acceleration ending at 11 meters per second, starting at 0 meters per second, then you're like, well, gosh, we would have to have a displacement of this, but the displacement was bigger. So therefore, it is not uniform acceleration. All right. Okay. Okay. Can we use kinematics equations then? Apparently not, right? The kinematics equations are only good for constant accelerations. The derivation of the kinematics equations come from a linear VT graph. In the previous problem 4, I kind of talked about it a little bit in passing, how we derive the displacement equation. But the linear VT graph, you're also going to get y equals mx plus b, and that would be v is at plus v naught, would come directly from that. And then the third one, v squared is v naught squared plus 2a delta x, we derive by just combining those two equations mathematically together, substituting through t to get rid of t. So the point is, yeah, it's not gonna, you can't use kinematics if it's not a constant acceleration. Which brings us to, now it says, if I could sketch the VT graph, oh look, if I was to sketch the VT graph implied by this data, let's say that we had, and this, I wish I'd made this a little bit clearer, right? Perhaps we'd say, okay, I need to have 40 meters as the area between my line and the time axis. A linear plot only gives me 27.5. I need more area. If, and I wish I'd said this, if we assumed a constant jerk, then the acceleration would be linear and the velocity here would be parabolic. Okay, does that make sense to you? You remember our graphs would go xt, vt, at, jerk time, right? And you say, hey, if this was a constant jerk, right? So it's a constant value. So this is proportional to t to the 0 power. Then going up this way, this is the derivative. A constant is the derivative of a linear, right? And we might have, in this case, this is a positive, and so this would be a positive slope. And so this would be proportional to t to the first power. It's a linear graph, right? And then this one would be proportional to t squared. So I take the derivative, I get t, first take the derivative, I get t to the 0, right? If it's proportional to t squared, then this is going to be like something parabolic, like so. And then this would be proportional to t cubed to be a cubic graph. But anyway, point is, right. The thing is, this might be like this. This is a concave up, right? So this is like a parabola opening upward. But we could also have something like this, where we'd have our graphs, right? And this time it would be a constant negative jerk, right? And then this would be a negative slope. And then this would be, you're like, oh my gosh, this is going to be a parabola that is opening downward type parabola, right? Okay, and then this would be, again, some kind of weird cubic. Anyway, but point is, you say, which one is it? Okay, which of these shape graphs are we talking about here? Knowing that we're going to start from 0, 0 and end at 5, 11, which way do I need this to curve? An upward opening curve or a downward opening curve, right? This parabola. And you say, well, gosh, I need to get more area, a bigger displacement than 27.5, so I need more area under it. So this is implying if we assume a constant jerk, I wish I had said something like that, then it's got to be, to get more area, it's got to be an opening downward type thing. So we get this extra area out here, right? Okay, so that this total area will add up to be 40. Okay, and so that's it. So it should be a downward opening parabola. Would give greater area under the VT curve, right, under the VT graph. Okay, so a greater displacement. Now, the fact is that we could have a graph that does something crazy, woo, right, and end up having a bigger area. You know what I mean? Woo, you know, who knows, right? But if I assume a smooth curve from a constant jerk, so that this is parabolic, right? Which way does a parabola have to open? Okay, so assuming constant jerk, a parabolic VT graph. Okay. All right. There we have it. All right. That's problem 5. There's other ways of thinking about it, but I think this is the cleanest way of getting to that solution. All right.